making a joke. I could care less.
Yeah. You were making Niles and Coca or something, whatever it was.
What?
You were making.
Like,
No, not
not
really.
wash my hair for like a week or something. What?
I mean, yeah, you could do that. I wouldn't recommend it. Okay. So we've been talking about rates, and the number one thing that we've been looking at to figure out rates was what? You said earlier. Concentration. Okay. Now we're gonna also talk about something that you have heard me talk about last year. But what other factors are going to affect the rates? One thing that should jump into your mind pretty quickly is the effect that temperature has on how fast. Okay? A chemical reaction is going to speed up when the temperature is increased. Now, the why behind that is going to come from the collision theory, which I'm sure you guys remember the collision theory. This states that for a chemical reaction to occur, three things have to happen. You remember this from last year?
They have to collide with enough force in the right way, facing the right way.
Because they could hit, but if the things don't hit that allows the two things that are going to react, if they don't hit, then you're not going to have a reaction. Okay? So if you remember, we talked about having to have enough energy. Do you guys remember the vocabulary word activation?
Activation energy.
Okay, we're going to do some graphs and some whatnot to kind of visually show this. Okay, so let me ask you a question here. Listen carefully. How does the collision model explain that a reaction rate depends on concentration?
More things close together are going to hit more often.
Yep.
The pressure.
The higher the concentration, the more stuff you have, and thus the more likely you are to have collisions. You increase the amount of collisions, that's just going to be, from a probability standpoint, it's going to increase the amount of properly oriented collisions, just from the sheer chance that you have more collisions. More collisions means more opportunity for them to be properly oriented. Okay? Next question. What does an increase in temperature? How is that going to affect a molecule's ability to react?
They're moving with more force. Number two.
Yep, they're moving faster. Moving faster simply just means there will also be more collisions.
Yeah.
And those collisions are going to have a higher...
But wouldn't adding heat some chemical reactions change the product?
Change the product?
Yeah, like change what product is formed.
I think so.
Or like the structure of the product is. Like,
There are some things that, like, the
Like
temperature
high
affects,
temperature
like, what
form.
type of crystalline solid it is.
Okay.
Like, you can have rhombic crystalline solids or like...
Okay.
Yeah, but that's not a chemical reaction.
Yeah.
Okay? So, the reaction rate is much smaller than the calculated frequency of collisions of gas particles. Why? So what that's saying is, just because they're colliding doesn't necessarily mean they're reacting. Why?
Because they might not be taking in the right direction.
Okay. So what we have is, anything that increases the amount of collisions is going to typically increase the rate. Okay? But not all the collisions produce a reaction because they have to be properly oriented. And even if you had a bunch of collisions and they were properly oriented, if you don't have enough energy, you're also not going to see a reaction. So, let's talk about these two guys, which you should at least remember seeing. I'm going to put it on a graph. I don't know, do you have space for a graph or no? No. Of course. Of course. Where's the back going here?
Underwater blindfolded.
She's working on her water blindfolded.
Left-handed.
Upward.
Involving stung by bees and eating. You can keep adding to it. Just in a moving car.
All the things to say, stung by bees.
Well, it'd be hard to think clearly if you're
Well, absolutely. I mean, you could have said like being stabbed by knives, but you said stung by bees.
I don't like insects that much.
Okay.
I went, oh, that'd be horrible.
My goodness, that is great. All right, I'm happy now.
Good, I guess.
I mean, I was happy before, but I mean, I wasn't happy I got my eye spitted. But
Now you are. You are thankful.
now I'm thankful. You know what? God tends to give you things
That you need.
right when you don't want them.
That's one which you need.
But yeah, sometimes it's okay. All right, so this hump, okay, that difference in energy is called what?
The activation energy.
Okay, and it's actually represented E sub A, energy of activation.
Okay.
Okay? What is this to this?
That is reaction. Reaction. I know there's a term for it.
It's really just the overall change in energy. And usually in a previous chapter we said change in H. Because isn't it products minus reactants, or the difference between the products and the reactants, and since it's a state function, it doesn't matter what happens in between? You guys remember that?
No, it doesn't
Yeah.
matter.
Okay? So really, this tells me it's exothermic, right?
Yeah. So it really
Because we
move
started at
up and
high
down.
energy, we ended at low energy. And so it might be easy for us to think, oh, it's an exothermic reaction, so therefore it's going to happen. Not true. I can show you an example of a endothermic reaction.
So it really could be doing that for all we know. It could be doing one of those for all we know.
Doubt it.
I know, but it could.
I mean, I doubt it. I don't want to say no, because I guess I don't 100% know, but.
Look, state function.
Okay, so I wanted to show you here how this whole thing is your energy of activation. And from here to here is your change in E, or you could say your change in H probably. Okay? It was actually the 1880s that this whole idea of an activation energy came about from a guy by the name of Svante Arrhenius. He's also known for something else that's really important. Do you remember?
I know
Remember that name? Svante Arrhenius.
Yeah, I know the
Svante
I don't know.
Arrhenius. He's very familiar. He did something else that's
Does he
pretty.
have an equation?
He has a model or a theory that's pretty important that we'll get to in a couple chapters. We haven't talked about it yet. This year.
I know the name.
So he came up with the very first acid-base model, Svante Arrhenius model, where he said that you're just transferring at H plus.
No, I thought that.
Okay. Let's open up your book. Turn to page 566. Oh, I probably should have put on that graph where the activated complex is. I didn't really talk about that. Well, do you guys remember that the
Activate. All your base are belong to us.
Okay, so if you remember, your activated complex is a transitional state. It's where you have your reactants colliding, and you're in the process of breaking old bonds and forming new bonds. So at that very short-lived moment, you're actually the most unstable you will ever be throughout the whole process of the reaction. when I say unstable, what should be running through your head when I say unstable?
Highest energy.
Highest energy, and that's why you're going to see your activated complex at the very top of your activation energy, or your highest point on an energy diagram, because you have an extremely highly unstable state while they're colliding in the process, which you can imagine that's not going to be a very long time frame, right? Right at the point that they collide, okay, so it's going to be very short-lived. Now I'm going to start reading. I'll start reading at the top. It says this question was first addressed by Mr. Svante Arrhenius. He proposed the existence of a threshold energy, which we call our activation energy, that must be overcome to produce a reaction. Such a proposal makes sense as we can see by considering the decomposition of BRNO in the gas phase. In this reaction, two BRN bonds must be broken and one BR-BR bond must be formed. Breaking BRN requires energy, which must come from somewhere. The collision model postulates that the energy comes from the kinetic energies possessed by the molecules that are reacting. Okay, so in order for them to collide, they have to move. The faster they move, the more energy they have, and that what he's saying is the energy of their movement is what causes them to have enough energy to overcome your activation energy. Does that make sense, everybody?
Yeah.
Okay. The collision model postulates that the energy comes this kinetic energy is changed into potential energy as the molecules are distorted during a collision to break bonds and rearrange the atoms into the new products. We can envision the reaction process above. The arrangement of atoms found at the top of the potential energy hill or barrier is called the activated complex or transitional state. The conversion between your reactants to your products is exothermic, as indicated by the fact that the products have a lower potential energy than the reactants. However, your change in E has no effect on the rate of reaction. Is that in your notes anywhere? Do I have anywhere in your notes that the change in energy has no effect on the reaction rate? Put it in. Remember, what is reaction rate talking about?
How fast it is.
How fast? So, I want you to put that in. The change in E has no effect on the rate of reaction. Why is that?
It's just fun. It's a state function. I don't want exponential.
Okay, that's true. I have an exothermic reaction and an endothermic reaction here. Where's the highest point of energy on both of them?
About the same.
I know, but like, it's in the process of overcoming what?
Oh, it's in the middle, so 5 months initial.
You know, what are we overcoming? What's the hill called?
Activation energy.
Yes. Okay? So it doesn't matter if you're exothermic or endothermic. From a speed standpoint, you have to first get over the hill, which is our activation energy. So I think the next sentence should probably say, rather, the rate depends on the size of the activation energy. So how fast a reaction is has no impact on whether or not you are exothermic or endothermic. It has to do with how high the hill is, because that's what you have to overcome for it to even happen. Okay? So your speed is going to be dependent upon your activation energy and whether or not you can get over it or not. Yes, we can talk about thermodynamically favorable versus thermodynamically not favorable, but that doesn't tell us anything about the rate or how fast it will happen. Okay? The main point here is that a certain minimal energy is required for the molecules to get over the hill so that products can form. The energy is furnished by the energy of the collision. The collision between the two reactant molecules with small kinetic energy will not have enough energy to get over the barrier. At a given temperature, only a certain fraction of collisions possess enough energy to be effective. Okay? So, what we have is this idea that the rate is going to be determined on being able to overcome or surmount the hill or the activation energy. Okay? So let's okay, this is just a vocabulary word. This goes back to step 3 of the collision theory. Step 3 of the collision theory is what?
Then it'd be facing the right way.
Okay. So you can have plenty of energy, and we've talked about this already. You can have plenty of energy in your collisions, enough energy to overcome the activation energy every single time. But that doesn't mean that every collision with enough energy is going to produce a reaction because of what? Orientation. Okay, I'm not going to elaborate on that. So here are really your two important factors that are going to determine if the reaction will occur. First thing, okay? Collisions must have enough energy. And they have to have enough energy because they need to overcome what? Activation energy. Second, they also need to be properly oriented. If you don't have both of these two things, it won't happen. What?
The second one's our catalyst is for, right?
That's one of the ways to help it out, yeah. So, here's Arrhenius' equation. Notice this equation has a very similar format as our previously 3 zero order, first order, second order equations. Why do I say that? It's the same format. What do I mean by that?
It has two versions.
Yep. Y equals mx plus b. So what is your y? What is your, I'll just do x here first. What is your x?
1 over t.
What is your m?
Activation energy, sorry, negative activation energy over rate, R.
R is your constant.
8.3145,
Okay,
okay.
that's also a very similar constant that we've used before. Okay, and you can put what your b is, but that's really not that important. Okay, so what's neat here is Arrhenius came up with another linear relationship where we can plug in and we can figure out what the activation energy is as long as we know what the constant is and as long as we know what the temperature is. That's all we need to know. Then we can figure out what is the certain amount of energy that I would need to give to surpass or to surmount the activation energy. So, I think I have a problem. Okay? Now, you could do, here's another way you could do this. I think I've already shared this with you, but if I want to know activation energy, technically all I would need to do is find the slope. Well, you have enough energy here to find your y and to find your x. Now you would have to take 1 over t to get your x, and you would have to take ln of k to get your y. So technically you would only need to find 2 points, and you could do that. But we're gonna do this on Excel. Okay? Did I give you a data table for you to put in what 1 over t is and what ln of k is, or no?
Yeah.
You have room on the sides that you could like do it like in the graph or in the, okay, yeah. So what I want you to do, is I want you guys to take 1 over t and put it next to t, and I want you to type ln of k and put it next to k. Actually, why don't I have same 3 here, I want you guys to do ln of k, and you guys do 1 over t. So this column here should be your 1 over t. Your x is up there. And your y's should be your ln of k. Can I get an amen to those numbers? I did those right?
Just a second. There we
I don't know. You look at
Wait, 1 over t?
0.05.
1 over 20.
This is ln of,
Shoot.
what's it called?
You read the T,
You
the
do L
K,
over
right?
T.
You
1
did-
over 20?
You did ln of k.
You guys didn't turn to Kelvin, sorry. My bad. I'm trying to tell you guys in Kelvin.
Wait, what?
Yeah, you need your temperature needs to be in Kelvin. I forgot to
But
let
those
you.
aren't temperatures.
This is 1 over T of the temperature. So you take 20 degrees Celsius, add 273 to it, so it's 1 over 293 should give you this.
Yeah.
Is that
Then
correct?
y is ln
Yes. So these numbers should look right. Those of you who are doing temperature, I forget to tell you that they need to be in Kelvin. And that has to do with the fact that your R has got units of Kelvin.
Wait, so temperature will be on the left then?
It'll be your X.
Okay. The chart.
Well, 1 over T, but yeah.
Yes. Chart.
So then I think you guys are pretty good at this point at remembering how to do this. Okay. So that should be big enough for us to see. Nice linear curve. So, if we want to find activation energy, which I believe is what we're trying to find here, correct? Your M, or your slope, equals, what was it, negative EA over R. Is that correct? So our slope in this equation is negative 12,236. Negative EA, and our R is 8.315. Is that the right R? 3145. I believe is a joule per mole K. This M must have units of K. I'm guessing. Okay, so why don't you guys solve for activation energy quick? The negatives are going to cancel, so you should have a positive number. And it looks like it's a decent amount of activation energy that you have to overcome.
One of the K values now. One of the K values.
What was that?
Wait, how did you find activation energy?
They just multiply.
Just
To multiply,
Oh.
and the negatives cancel out. So really, you're just multiplying those two. Should give you what? Basically 1.0 times 10 to the fifth joules per mole. That is going to be your activation energy for this particular thing. So that's a relatively large activation energy. You're going to need a good amount of energy of collision to get this guy to actually react. Okay? Questions on that?
Just always has to be calculated.
Yep, sorry, I forgot to mention that. It needs to be in Kelvin because of your R value. It's very similar process to finding out what our zero order, first order, second order is. Okay, very well could on a test make you just figure out what the order is, what the reaction rate is, and then make you figure out what the activation energy is, all for the same problem. Okay? The next problem, which we aren't gonna have time to do,
Was that Jules?
joules per mole, yep. We're not gonna have time to get to the next problem, but I'll show you the equation for it. It's just a modified modified version of what I just showed you. So this is comparing two different, because if you have two different temperatures, you're gonna have two different rate constants. The rate constant is gonna change with temperature. So on this next problem, this next problem, it wants you to find the activation energy when you're given two different Ks and two temperatures that go there. And you would use that equation that was on the board. Okay? Questions?